Okay, thanks. It's been daunting following that 2.5-hour talk, and I'm going to change gears completely and talk about seismology. In some ways, my talk, I guess, is complementary to Doug's, in that Doug talked a lot about attenuation, and to some extent also to Kai-san, but I'm going to talk more about the effects of anisotropy on seismic wave propagation in melt-filled areas. I initially wanted to talk a little bit about ideas of sulfide melts instead of silicate melts, but didn't see much of a petrology theme here, so I've kind of gone more to just actually seismic methods. And the first part, I'm going to describe some of the effects of melt on seismic properties, and the second part, I'm going to concentrate on observations that we have from Ethiopia. So we've been working in Ethiopia for over 15 years now and arranged a whole series of seismic measurements, and I think individually and more usefully combined, they really are help us constrain aspects of where the melt's located and its geometry and stuff. And I guess if there's any message in this talk is that seismology is actually, and I think Doug said the same thing, it's very difficult to get out melt fractions. What we're much more sensitive to are aspect ratios, in fact a lot more sensitive. And I'm not going to talk much about attenuation, which is obviously something else that we're very sensitive to. So I'd just like to acknowledge my co-worker, James Hammond, who's done a lot of this work. And I'll acknowledge other people I've collaborated with as the talk goes on. So we've talked about this a few times, that the distribution is very influenced by the wetting angle or the dihedral angle. And this, depending on what the dihedral angle is, if we have the melt in more isolated spheres, we get a very different effect than if it's in tubules, and at very low wetting angles, we can think of the melt as being oriented in films. And so this will affect things like the permeability, the rheology of the material, the conductivity, which is important for things like MT surveys, and the seismic velocities. And then if there's a degree of alignment in the films, for example, or the tubules, all of these properties will have an anisotropy. In other words, a dependence on direction. Hey, Herbert. And there is evidence for alignment in melt distributions in both laboratory and field studies. This is early work by Ulrich Fall showing alignment of films. This is work by Ben Holtzman and Dave Kolstad and co-authors showing sort of the alignment of the shear bands that we've heard a lot about this week. And then at even larger scales, we get a preferential alignment in things like dikes, vertically emplaced. This is a picture from Iceland. And the important thing to realize is that when we get down into the upper mantle, the seismic wavelengths are really long. And so what we see is effectively, we can think of an effective medium that is homogeneous, but because there is this alignment, this texture to the medium, it's homogeneous but anisotropic. So even though there's a lot of detail in these, a seismic wave won't see that, and so we can treat the medium as an effective medium. And I'll say a bit more about that in a minute. And so what we need to describe is the stress-strain relationship, which is described by the stiffness tensor, which is a 3 by 3 by 3 by 3. Or we can describe it by a compliance tensor. And what I'll argue a bit later is that actually compliance is much more useful for adding the effects of aligned cracks, pores, or inclusions. But there's a lot of different competing effects going on, and this is one of the challenges I think seismology really has as to how to untangle one from the other. So we know that the seismic velocities will be sensitive to lithology, and we know that many minerals will align in response to flow or deformation by dislocation mechanisms, so that leads to a lattice preferred orientation. We know in fluid-rich materials that there's poroelastic effects, and pores can be oblate or aligned in either banding or in flat pores. We can get banding of shear banding, which we've talked about. And then in the shallower crust, we can get aligned cracks and fractures. And generally, all these mechanisms will affect the seismic velocities, and they can all cause quite significant seismic anisotropy. I'll just make a note that our compliance tensor or our stiffness tensor can be, because of symmetry in the stress tensor and the strain tensor, we can reduce it to a 6 by 6 Voigt notation, which will come up a bit later. And so the challenge is that we're looking at things that affect seismic velocities and seismic anisotropy on many length scales. So right from the crystal scale, grain scale contributions will be the alignment of melt films or tubules, and then on larger scales, either fractures, dikes, or layering in the earth. And so to try and include the effects of these melt films, we can think of the melt films as being an additional compliance term, a perturbation to the compliance matrix. And if we know enough about the medium, we might be able to describe the lattice preferred orientation. This is the type of things that we're able to do now in oil reservoirs, where we can actually get samples of rock, measure the petrofabric, and then include the additional effects. So it's a perturbation, and there's quite a bit of theory behind this, which goes back to Budiansky and O'Connell. Sayers and Kachanov incorporated the effects of aligning these inclusions. And so if the inclusions are all aligned in a particular direction, in other words, the normal to these films is in x1, we can think of this perturbation or this additional compliance as being an additional compliance normal to the inclusion, or the pore or the melt film, and tangential to it. And if the material's intrinsically strongly anisotropic, these two terms will be different, but for most cases we can assume that that these are the same. For a long time, people assumed that this ratio was actually 1-to-1, which is called a scalar crack condition, but increasingly we know that that's actually not at all true.
If it does some component to depend on stress, you said, right? Then it becomes a non-linear material.
Exactly, yeah. Yeah, it can have a nonlinear component, yeah. So the anisotropy is controlled by this compliance, actually, and in really good data sets with very good coverage, you can actually invert for this normal and tangential compliance. We're a long way from being able to do that in mantle and lower crust, because we just don't have the coverage. But like I said, in oil fields, this is becoming possible. So the effects, so we can think of an idealized inclusion of melt, and it will have this normal compliance, in other words, how easy it is to squeeze normally, and then tangentially. And once you add fluids or melts, this inclusion could be higher, it could be stiffer or less stiff. But once you start to add fluids into these inclusions, it reduces the normal compliance more dramatically than the tangential. And then the ratio is actually very sensitive to how well connected these inclusions are, or how porous the medium is, or the viscosity of the material, and even the frequency of the seismic waves that image it. So basically, as we start to go towards low wetting angle, where I'm calling them fractures, but these melt films are all connected, the fluids can drain, the low frequency limit, this ratio goes towards 1. And this actually simplifies the style of anisotropy, which I'll show you in a second. So what I've shown here, this is the wave equation for inhomogeneous anisotropic media in the frequency domain. So here's our elastic stiffness matrix density, and we're solving for displacement. And if we assume that we have a homogeneous medium and plane waves, or another way of saying that's a zeroth order asymptotic solution to this equation, we get out the so-called Christoffel equation. So we'll be solving for a given direction, a given normal, and these are density normalized stiffness tensor. We'll solve for the phase velocity, and there's in general 3 phase velocities that fall out of that equation. So for the fully anisotropic case, we'll have a P wave and 2 independent shear waves which propagate at different speeds and with different polarities. And obviously one will be faster than the other, but that can vary as a function of direction. And in general, the ray direction and the normal to the wavefront, so this is the group velocity and the phase velocity, and the particle motion, if it's a P wave, are not coincident in the anisotropic case. And in general, it takes 21 independent elastic constants to describe this. But there's a lot of simplifications that can be made to that. In contrast, in the isotropic case, this is a degenerate case where 2 of the eigenvalues of the Christoffel equation are the same, and we just have a single P wave and a single S wave. And in this case now, the ray direction, the normal to the wavefront, the particle motion are coincident. And it just requires two independent elastic constants, the familiar Lamé parameters, to describe wave propagation in such a medium. But as I said, even in the anisotropic case, it's very difficult to deal with 21 independent elastic constants. So we often simplify things. So if we think of the case where we have melt films that are aligned in a particular direction, we can actually reduce it to a hexagonal symmetry, which only requires 5 independent elastic constants to describe wave propagation. And this is very commonly known as a transverse isotropy. If the symmetry axis for that hexagonal symmetry is vertical, we call it VTI, and if it's horizontal, we call it HTI. And this leads to some interesting effects. Obviously, the P wave this is velocity, so this would be vertical and horizontal. There's a directional dependence in the P wave velocity, but probably our most unambiguous observable or indicator of wave propagation in anisotropic media is the propagation of two shear waves. So if our normal and our tangential compliance for our melt film or our inclusion are the same, we get a very simple form of the anisotropy. It's called an elliptical anisotropy. And essentially the melt films become more and more isolated or not connected, or if we go to higher frequencies, we start to get crossovers on the shear wave sheets. And again, we haven't seen this ever in the deep Earth, to my knowledge, but it has been observed in a few data sets, VSPs and microseismic data in oil fields. And if we get very extreme cases where there's a huge difference, very isolated but planar inclusions, we can even get a triplication, a folding on the wave front. So this is just sort of I guess in a sense, a bit of a theoretical curiosity. But as I said, the really useful thing is the observation of the two different shear waves. And this is now used very routinely to look for anisotropy in both the deep Earth and the shallow Earth. If you have an incident shear wave in an isotropic medium, polarized in some direction fixed by the source, when it impacts enters an anisotropic medium, it will split into two orthogonally polarized shear waves, which will propagate independently. And we can measure how far apart these two shear waves are, and that gives us an idea of the strength of the anisotropy and the path length of the region. It's a bit of a non-uniqueness there. So what we can do is from a forward modeling point of view, is consider how some background material or rock that may have melt in it, and how the seismic properties might be influenced by the shape of the melt. So for example, if it's in flat inclusions, which would be like a low wetting angle, or more spherical pores, which would be a high wetting angle, or somewhere in between in tubules. And that allows us to then model what the wave propagation would look like. So these spheres show P wave velocity as a function of direction. So in this case, there's a really dramatic variation in P waves are much faster in a girdle, where it's blue here, and slower in the symmetry direction perpendicular to that. When the pores are spherical, we just get an overall reduction in seismic velocity, and it's not direction dependent. And tubules, we get a mild anisotropy. And what we can also plot here is the amount of shear wave splitting, and the little ticks on here, which are probably a bit difficult to see, show the polarization of the fast shear wave. And essentially, that in shear wave splitting, what we measure is essentially the degree of separation between the two shear waves and that polarization direction. So there's some systematic differences that are dependent on the style of the inclusion. So here, if we just look at how P wave velocity, for example, varies as a function of melt fraction, we can see actually how dependent this is on this effect. And this, is my initial point, that we're actually more sensitive to the shape of the inclusion than we are to the amount of melt that's in the system. And so, for example, we get a huge, 3, 4%, 5% reduction with only 1 or 2% melt fraction, whereas if we have spherical pores, high wetting angle, we get a much more modest reduction. Another, and what I should say also, that there's this very strong sensitivity to shape, but there also is going to be sensitivity to temperature, composition, and attenuation, which I'm not going to talk about so much. Another observable or indicator we use a lot to argue for the presence of melt is the VPVS ratio. So high VPVS ratios are used as an indicator of that. So here we're showing two examples, one where the inclusions are horizontally aligned and the other where they're vertically aligned. And if the inclusions of melt are in spherical pores, the VPVS ratio doesn't vary at all with melt fraction. You can add as much in there and it doesn't change VPVS at all. If the melt's distributed in tubules, either horizontally or vertically oriented, we will get a small increase in VPVS, but I would argue that's well below detection thresholds with seismic data. And in this case, we'll have actually, depending on whether it's the fast shear wave or the slow shear wave, slightly contrasting VPVS. Then if we go to flat, oblate, spheroidal inclusions, now the VPVS ratio becomes very, very sensitive to the amount of melt. And so even having horizontally aligned sheets of melt or inclusions, we get this significant rise to a VPVS of 2 for a fairly modest aspect ratio. And when the case where it's vertically oriented, we can get VPVS ratios that get up to 2.3, which are really extreme cases, but what I'll show you is we see VPVS ratios that get up that high in Ethiopia. And the only way to really explain it is oriented, vertically aligned melt films.
Just for clarity, the tubes have an aspect ratio of 100?
In this particular example, yeah, you can make them, whatever you want. Yeah, obviously the effect gets more extreme the more pronounced that aspect ratio is.
Horizontally or vertically, you just turn the picture, right? 90 degrees. Or you turn yourself. What exactly it means?
Well, this is saying that the effect is not as dramatic in this case, but it's still very appreciable.
And to take horizontally and make it vertical, I just
Yes.
flip, right?
Yeah, exactly.
Okay.
Yeah. But
So, Mike, when you're talking about the VPVS ratio, are you talking about the propagation in a particular direction, or are you
Yes.
talking about the overall average?
no, I'm talking about a directional dependence for vertically propagating waves in this case.
Okay, so
Yeah.
you're assuming
Yeah,
vertically
sorry,
propagating waves for
I
both
should have said that.
ENS.
Yeah.
Okay.
Yeah.
Oh, one more question, clarification. When you say alpha very small, are you talking about like a melt film?
Yes.
Okay.
Yeah. Well, because it's an effective medium, it could be a melt film, but it also could be stacked sills. And I'll come on to that actually. We have a hard. One way well, this is getting way ahead, but one way we can actually start to address that is by looking at the frequency-dependent nature of the anisotropy. So obviously one of the challenges is, well, okay, this is all well and good, but how do we distinguish this from the effects of lattice preferred orientation, which we know is very well developed in peridotites, for example. So here's an upper hemisphere projection of what the P wave velocity would be like, the shear wave splitting, and then this is the shear wave splitting showing the orientation of the fast shear wave. And this is for isolated oriented melt pockets. So it's a particular example, it doesn't really matter whether it's realistic or not, but it sort of shows you that for a vertically propagating wave, we'd have a fast P waves, we'd have something like an SKS wave, a body wave coming up from below would be oriented in this direction, and that would have that orientation and maximum amount of shear wave splitting. In contrast, if you look around the edge, so if you were looking at this with surface waves, and this is what I'm going to show you in Ethiopia, is how we can use different waves to try and pull this apart. We get a very characteristic variation between the vertically polarized surface wave and the horizontally polarized surface wave, or the Love and the Rayleigh waves. And so along this direction, we get maximum splitting. This is would be in the direction of the alignment of the inclusions, and then there's a crossover in this particular example. In the case, this is taking some actual elastic constants that Alan and Andrea measured for Tanzania, and looking at this is what you'd get for a real rock due to lattice preferred orientation. So quite a different P wave velocity variation, but again I would argue that the shear waves are an easier thing to look at for the anisotropy. And what becomes confusing is it would give you a very similar SKS result. But by looking at horizontal wave propagation, looking at the edge of this circle, we actually get very different behavior. So in the direction of the olivine A-axis alignment, we get virtually indistinguishable difference between the SV and the SH wave, and it gets larger as you go to more oblique angles. And I'll show you an example of that in real data in a minute. So to explore this, I guess, a bit more, the different things, the different aspects that can cause anisotropy, I worked a bit with Ben Holtzman, looking at results from his experiments in the lab to try and predict what the effects would be due to both the lattice preferred orientation in the deformed peridotite, aligned melt inclusions, which are, I mean, we talk a lot about the shear banding and stuff, but actually there's very small amounts but pervasive amounts of melt all through the material, and it is highly aligned when he looks at the structures. So that's another effect, just aligned melt inclusions. And then finally, a more macroscopic effect due to the layering of these anisotropic but melt-rich and then melt-poor bands. Okay, so there's sort of three different contributions coming in. What was interesting in this experiment, which is, I don't want to go into too much more beyond this, is that actually the orientation of the A-axes aren't in the direction of shear because of the melt segregation and the strain partitioning. The A-axis of the olivine actually aligns orthogonally to what we normally think of it as aligning in this sort of deformation regime. And that contribution from that, I'll show this more simply in a minute. We can calculate the predicted P-wave velocity as a function of direction and the shear wave splitting as a function of direction. This is if the A-axes are aligned vertically or horizontally, because we don't know whether the shearing will be horizontal or vertical, and in fact it could be even at an oblique angle. But we can at least get an idea of the magnitude of the effect. So again, this illustrates the importance of the aspect ratio. So what we're plotting here is that there's very low volume fractions observed in Ben's experiments of melt, but it has very small aspect ratios. And what this is showing here is aspect ratio and the amount of shear wave splitting as a percentage for a vertically propagating wave. I've called it SKS. So this is one of the seismic phases that we use a lot to image anisotropy in the uppermost mantle and lithosphere. So this is a shear wave through the mantle, it converts to a P wave through the core, and then back up as a shear wave, and we can use that to study anisotropy in that area. And these are the hemisphere projections for the P waves and the S waves. But this is sort of the more interesting diagram, and what's shown here are different volume percents in other words, amount of melt. So to get, let's say, 4% shear wave splitting, you could have it with very low aspect ratio, sort of 0.15 with 2% melt. In contrast, you could go to an aspect ratio of 0.01, which is really more the regime that he's observing in his experiments, and you only need 0.1% melt. So there's this, this effect is really, really important, and it's why it's so difficult, I think, for seismology to pull out volume fraction, and that we're so sensitive to this aspect ratio. And then the final effect is like a Backus-style averaging. So George Backus in the early 60s showed how the mathematics behind developing a VTI-type fabric, a transverse isotropy, from the layering of materials with contrasting stiffnesses or elasticity. And so we generalized this for anisotropic layers, so where we could incorporate the LPO anisotropy and the small volume fraction but low small aspect ratio inclusions, and then to put in the more macroscopic effect of the melt banding. And so I'm not saying this is exactly the same, this is quite different, but it's this sort of scale of regularity in melt-rich bands of material. And so obviously how significant this is depends on to what, the size of the layer, the melt-rich layer to the melt-poor layer. So here 0.5 is unrealistic. That says the melt-rich layer is half of the material. And then how much melt is in the melt fractions in those bands. Okay, so if for a 0.1, 0.2, you get a very small effect for very low melt fractions, but as it goes up, it can get more appreciable. And to be honest, I don't actually know, I don't have a good feeling for how much melt fraction you can get in these shear bands. And so then when you can add this all up and look at the relative contributions, and the punchline, I think, is that the biggest contribution is this background small volume fraction, but small aspect ratio oriented melt pockets. The layering can be effective, but only if you get very high amounts of volume fractions in the melt bands. And the LPO effect in this case is smaller also, so most of the contribution comes from this area. Okay? So the problem we have with real observations is how do we, we just look at the crude, we have a measurement of this, and we're trying to understand what's causing what. And so the approach we've taken, which is probably way oversimplifying things, is that what we're dealing with primarily is either melt-rich material that's horizontally oriented in stacked sills, as shown here in Katrine's model, or in near vertical, perhaps marginal to boundaries, or in the shallow crust, vertically oriented, because that's the favorable stress orientation for fractures and melt to get out at the surface. And that's kind of the approach we've taken to try and pull apart the Ethiopian data. So we're dealing with either looking at an HTI fabric, so this would be the aligned vertical melt pockets, or a VTI fabric with horizontal sills. And so to really be able to look at these two things, we need to look at seismic waves that propagate in many directions through such a model. So just a vertically propagating wave isn't going to tell us enough. And so the first thing we can do is look at tomography, just try to identify where there's low velocity bodies. And this can be done with body waves or surface waves. We can then look, if we can do this for both P waves and S waves, we can start to look at VP-VS ratios or R values. And then another approach is to look at receiver functions, so how a seismic wave converts and reverberates at a discontinuity. So the most common one that this is used to study is the MOHO. And then anisotropy, so this could be azimuthal variations in shear waves, or the Love-Rayleigh wave discrepancy, differences between vertically and horizontally polarized Love waves, shear wave splitting, and azimuthal variations in PN waves. So this of course was the approach that was used by Hess and others in the 60s to first look at mantle anisotropy. And what we haven't really got around to doing yet is attenuation mechanisms. So just coming to this workshop's kind of given me good incentive to have a look at that, actually. So I'm not going to talk about this in much detail, but this is kind of, depending on whether you're looking at a PN wave or a Rayleigh wave or a Love wave or shear wave splitting or receiver function, you can take the observation, and so in this case the observation is P wave velocity, and look at where you sit in melt fraction versus aspect ratio. Or, for example, a Rayleigh wave, you could look at SV anisotropy and see where you sit in that space. And in each one in isolation is going to be incredibly non-unique, but when you start to add them all up, you start to, you can kind of, you can rule out parts of this parameter space. So it still gives us some uncertainty, and I won't go into too much detail, but it's a lot better than we've been able to do previously. And so we can look as a function of depth and also laterally variations in how melt might be distributed in a particular system. So I'm going to now show you some examples from Ethiopia. This has been an exciting place to work. This is a feature, this is a segment of the rift in the Afar region of Ethiopia. It's called the Debahu Rift, and this segment of it, 80 kilometers long, opened in 2 weeks. And it's been attributed to repeated dike injections that have, I think we're at our 14th or 15th dike injection, and this has been observed. What's also exciting about it is it's the first time this sort of evidence has been observed in the time of satellite geodesy. So INSAR, for example, and Tim Wright's work and co-workers have been really influential in this. And so what we got interested in when we first started working on this was sort of trying to understand continental rifting and what sort of, how seismology and other magnetotellurics, other geophysical techniques can help offer constraints. And so I guess this is your conventional idea of continental rifting. The plate responds to distant forces, maybe with some heating from below from a plume, and you get a very distributed strain or deformation across this region. And these are calculations from Roger Buck, but to break this thick, cold continental lithosphere, you need something on the order of 800 megapascals. I don't know how much uncertainty there is in those sort of measurements, but a lot. And so when you look at what the forces are available for rifting, this has been known for some time now. You can look at the effects of distant subduction, gravitational potential energy, or dynamic topography, basal tractions, either compressions or extensions associated with underlying convection, and then pre-existing weaknesses or lithospheric thin spots. If you add all that up, the forces are insufficient to actually come up with that 800 megapascals. And so melt is kind of crucial to facilitating rifting in this area. And so again, this is a picture from Roger showing if you start to get melt injection, it really focuses the strain, the deformations over a much shorter region, and it reduces the yield strength very, very dramatically. So all of a sudden, it doesn't take as much force to start continental rifting. And so this is actually this is an old slide. This is 15 years of fieldwork in Ethiopia. But there's a lot of organizations have been involved, American, UK, French, and the big players are the Ethiopian and Eritrean institutions, because without their cooperation and help, we really would not have been able to do any of this. And the other good thing about this project is it's trained a lot of young scientists in different components of the project from different institutions. I think Manilow, James Hammond, and Ian Bastow cumulatively have spent something on the order of 2 years in the field working in this area. So it's a really substantial amount of time. The field work's really interesting. It's an exciting place to work. Most of the time we get around by truck. I wasn't lucky or unlucky enough to get around by camel, but there's been some pretty remote areas. This is a network that was put on the Nabro volcano in Eritrea, which erupted in 2011. It was the biggest emission of sulfur since Pinatubo, and it was only because of seismologists on the ground there. 10,000 people were evacuated from this area, and there was a 30-kilometer long lava flow as a result of the eruption. So this is putting in a station shortly after the eruption. And so since we started working there, when we first went there, there was a geoscope station in Djibouti and an IRIS station near Addis Ababa. And since that time, we've deployed cumulatively, working with this is everybody involved in the many different projects over many periods of time. There's been the deployment of over 200 broadband 3-component seismometers in the regions. And when we first started working there, we sort of had to concentrate on the main Ethiopian rift, but increasingly we were able to move more into Afar and then into Eritrea, and actually more recently, Derek Keir and others have been working in Yemen. So actually the ability to do the field work has really changed dramatically. A lot of it's just instrumentation improvement, which has been pretty good. So this is to give you an idea of sort of how this can change your picture of things. This is I can't remember which tomographic model this is. I think it might be one of Jeroen's, but it's this is what the shear wave velocity structure looks at a depth of 75 kilometers when you just use essentially those two stations and a global network. And this is the picture that we have now. So it's very easy to say there's an Afar plume there when you see that picture, but actually when you start seeing this picture, it's not so clear. It's a plume anymore. And in some ways, it's the most expensive experiment to tell you where the rift is. We can see this very, very focused low velocity zone at a depth of 75 kilometers. It does this abrupt left hand, then a right hand, and actually the more recent images show it going up into the Red Sea.
Have you got images deeper?
Yes, coming up. Just as a point, we know this area is anomalously slow for a long time now. The station at Addis Ababa has got the slowest travel time residuals of any station on the planet, actually. So as you go deeper, so here's a cross section going across this way. you can see how there's this low velocity zone that just cuts like a knife through butter up through this region, and then below it fans out. And then looking along strike in this direction, actually it's like a carpet of low velocity material that lies below sort of 200 kilometers. And our initial interpretations have been that this is associated with the density flow from the deeper superplume structure, and these punctuated upwellings are melt related. It's not proof that it's melt yet.
Can you point out the BB prime profile on the map?
The BB prime is right. I thought it was through here, but on the map it looks like it's through there. It's up there.
That would make more sense because you have the
Yeah.
narrow channel.
Yeah, that's right, because it's cross-cutting that bit there. Yeah, it's right there. Yeah.
This is P waves or this is surface waves or what?
These are shear wave body waves. Yeah. And so you can cross-plot the travel times for the shear waves and the P waves. So this is one way you can argue that this has to be melt related, and this you can come up with this R value. What you can't do is divide one image by the other, because the Fresnel zones and the frequency content are very different and the resolution is different, and that's a good way of introducing artifacts. But as a simple proxy, you can just sort of cross-plot the travel time residuals. And if it's thermal, you'd expect travel time residuals to lie along a line like this. Previous work in the Rio Grande has this dotted line, and for stations in the Rift Valley, this is sort of the best fitting line to our residuals. So it's a really extreme R value that we're getting in this case. And in fact, I should have put in a picture from Takai's JGR paper, which the results we get are actually above her theoretical limit. Doug?
Mike, what is the R value there? Because attenuation can really affect the R values beyond what you would calculate with poroelastic.
Yeah, no, if I remember right, we're getting an R value of about 2.3. And again, hearing these talks this week, it made me think we really got to start considering attenuation. But even still, it's going to be hard.
Yeah, 2.3 is very high.
It's going to be hard to get around. Well, we have 2.3 independently through another method too, which I'll show you in a second. So, which is this method.
But is that the main evidence you've got for melting being, melt being present?
No, I'm building up. I'm building up a story here, Dan. Just hang on. So here what we're doing is looking at receiver functions, okay? So these are these conversions at the crust, and this is just showing the thickness. So when you're under the plateaus, we get very thick a crust, 40 kilometers and above, and as you move into the main Ethiopian rift, it drops to about 30 to 25 kilometers, and then it just progressively thins as you move into a far. So here you're going from the highest mountains in Ethiopia, Ras Dashen, 4 kilometers above sea level. Here we're 100 meters below sea level, and there's the crust thins to almost 15 kilometers at this point. And so what's happening at the base of the crust is more dramatic than what's even happening on the surface of the Earth. And when you look at the VPVS ratios, again, we don't have quite this is accentuated. We get good coverage because there's lots of refraction profiles, wide-angle reflection profiles. When we look at VPVS, we get, again, sort of more modest expected VPVS ratios, 1.6, 1.7, 1.8 under the flanks. But as you move into the rift, under the magmatic segments, and then up into a far, we're getting up to 2.2, and then, some spots almost 2.3. And again, the transition's super sharp. So it's supported this idea that the melt's really focusing the... And we can do tricks like common conversion point migration, which is sort of a standard technique in exploration now. And I'll just show you one example along this profile from here. So this is the highest point of Ethiopia to pretty well the lowest point. And here's our common conversion point images. So we get this really dramatic drop to very thin crustal levels. And actually very simple, surprisingly simple results. And we get VPVS ratios that are sort of normal under the Western Plateau, and then well above 2, which we interpret as crust with partial melt. Put it in perspective, this is sort of the VPVS you get for a whole range of assemblages. Here's what you get at the Pacific Rise. Ethiopia is all up in this area here. So again, I would argue this area is chock full of melt. And we can also try and look at this, I'll try and go through this a bit more quickly, is we can look at the effects of anisotropy on receiver functions so that it kind of distorts our nice clean deconvolved signals. And what this is, the standard sort of so-called HK stacking, where we try to invert for an average VPVS and an average crustal thickness. In the anisotropic case, we get, for simple crust, we get a simple result. But once you start introducing anisotropy, it blurs things. So there's where the answer should be, and it's leading to an answer that way. And James Hammond actually published a paper on his own a few years ago that really tore this apart in some detail, looking at both the HTI and the VTI fabrics. One of the big indicators that you've got HTI fabric is that you've got a strong receiver function signal on the transverse component. The caveat to this is you can also get it with dipping structure. So it's, but an interesting case is, well, how does it affect HK stacking? And actually, it affects it in a, if you've got good enough data coverage, you can look at how it varies as a function of direction, and which is clear. This is a synthetic example which shows it quite clearly, but it also leads to underestimates of VP and an underestimate of the crustal thickness. If it's our horizontal sill model, we shouldn't have any energy on the transverse component. It still leads to an overestimate of crustal thickness, but there's no back-azimuthal variation. And what he's done is he's devised a way of trying to deconvolve or invert for both the VTI and the HTI contribution. And so some of these areas, I won't go into this in detail. I think the data are good enough to sort of pull out a contribution from both. And where this becomes useful, so this Kathy Whaler's group, DeCissi et al., this paper shows the magnetotelluric anomaly, and this is where the MOHO is, and superimposed on here is where the MOHO is from the receiver function, so that's why we know it's at the MOHO. And there's this incredibly conductive anomaly down in this area. Based on the combination of this with the receiver functions, the interpretation is these are stacked sills. It's a VTI type melt inclusion, so we've got these horizontal layers of sills in this region. This is the interpretation. So I'll now quickly go on to the shear wave splitting. Gareth showed this image from the East Pacific rise, again looking at these SKS phases, SKKS phases. This is sort of for simple two-dimensional flow, you'd expect the fast orientation of the anisotropy just to be in the direction of the olivine A-axis alignment. And this is what we expected to see in Ethiopia. And of course, we didn't see that. It was completely orthogonal to that. In fact, it parallels the border faults really well, but then there's a really systematic shift to follow the magmatic segments, which is a bit difficult to see in this plot, but it follows that. But the other thing is that the amount of anisotropy is huge. So on average, you get about 1.4, 1.5 seconds SKS splitting worldwide. Some of these stations were getting over 3 seconds. And we're seeing a lot of variability depending on where we are in this system. So again, this isn't proof positive that it's melt, although it was, I think, quite convincing. But then because we have, like in the subduction zones, we actually have earthquakes right below the region, we can start to look at how the anisotropy varies as in location. So these are fairly deep earthquakes under the Western Plateau, and they show like tiny amounts of splitting. You can explain all of that by just shallow crustal oriented cracks. This is Bosset, which is the magmatic segment that produces more melt than any other, and we've got a huge amount, up to 8% anisotropy under this region, and again it's paralleling the rift segment. We then move into this area and we get this again, this left-hand bend to follow the Debahu rift segment, huge amounts of splitting in shallow earthquakes in this area, which again we interpret as melt. You move off just to the side and a huge drop. So it's very hard to explain this without invoking something associated with the magmatism and volcanism that we're seeing at the surface. Also high amounts along the border faults, below the border faults in these areas.
What does that double arrow on the lower right represent? 5% anisotropy?
This is a scaling. So essentially that's what 5% anisotropy would look like. So that's much greater than that. These are much greater than that.
But over what depth?
You take the amount of splitting and you normalize it by the depth.
And what depth
Well, they vary. Like these earthquakes are 20 kilometers deep.
Oh,
these ones are 8 kilometers.
Those are
deep.
from local earthquakes.
These are, sorry, I should emphasize that. These are all earthquakes that are effectively right below the station.
So they're all above the mantle. I mean,
Yes, these are all above the mantle.
You're looking entirely at
In this case, this is all crustal.
crustal and
Yeah. In this particular case, yes. In the previous one, this is not. These are 3 seconds of splitting. These are like 0.2 seconds of splitting. So there's absolutely massive difference between the two of them. And the final piece of the story is to go back to what I said before, is to tell the difference between an LPO type model and a melt model is to look at horizontally propagating waves, so surface waves. So what we did is we looked at high frequency surface waves that transit the main Ethiopian rift, and we get down to about 80 kilometers. So we're into the mantle quite convincingly. In the upper parts, SH, above 10 kilometers, SH is faster than SV, and that's what you expect for layers of lacustrine sediments, volcanics. It's just a simple VTI fabric. Below that, we've got this very characteristic, and this every 5 kilometers we see exactly the same, and it's a huge amount of splitting where SV is much faster than SH along the rift direction, and then there's a crossover at more oblique angles. And that you cannot explain. You have to take into account the SKS and the surface wave. We can't explain that with an LPO mechanism. The only way that really fits is with some sort of oriented melt pockets, oriented melt inclusions. Okay, so that's the final, I think, sort of piece of this. And then the next step then was to say, well, okay, we probably got a layered anisotropy. So the melt's going to be from where melt's formed upwards, silicate melt at least, but below that there's going to be a contribution due to the density-driven flow. So we used a method that James Wookey developed for doing shear wave tomography, which a few other groups are doing now too, to try and divide this into different domains. And it's one of these things that's a lot easier said than done. So initially it was to try to divide the whole region into different tiles or domains, and then it was do them individually, and then try a homogeneous structure, but anisotropic, but a function of depth. And to cut a long story short, the net result was that below about 100 kilometers, this is the tomography, shear wave tomography at a depth of 300 kilometers. So there's that big, broad, red, low-velocity carpet, which is going towards Arabia, and has been interpreted as even propping up the western flank of Arabia through density-driven flow. The anisotropy is all completely aligned in that direction, and it contributes about 1 second of shear wave splitting to our measured SKS. And then, I'll just skip over this, then, well, it's kind of hard to see this, but then the interpretation is that we've got anisotropy that's locked into isolated slivers of continent above that, so the Danakil microplate, but there's other slivers. And these show up in the surface waves and the PN tomography also. And they contribute very low amounts of anisotropy, and where it's really high are right where all the magmatic segments are. Okay, so we've got this kind of Pan-African fabric in the lithosphere in the crust. We've got this density-driven flow underneath, and then it's all punctuated by these melt inclusions. And in the main Ethiopian rift, they're primarily vertical, and that's because there's very little room, and it's all trying to get out, and that's where the highest anisotropy is. And as you move into a FAR, it's all accommodated in these broader horizontal sills in the lower crust. And then very finally, because Shun talked about this, we actually looked at the transition zones. Okay, because the other big thing is like we're looking for the Afar plume that everybody's talked about for decades. So we're not seeing it really. It's something that looks like a conventional plume. And so we thought, well, we'll look at the 410 and the 660 kilometer discontinuity for structure. So if there's a hot plume going through that region, the 410 should be depressed and the 660 should be elevated. And we had really good coverage throughout the whole region. Really nice data. And what's interesting in general is very little evidence for a 520. It's a very clear 660 and a very clear 410. These are the stacks as a function of move out, and this is time, and this is work that Dave Thompson did, who's now at Cardiff actually. and very weak evidence for 520, but a very pronounced low velocity zone on top of the 410. But when you look in cross section, there's your 410 and your 660, and if you just calculate the travel time between these two, it's not varying. This is where we have a low velocity anomaly going through. So what's interesting about this low velocity anomaly is it doesn't seem to be temperature related. At least if it is, it's not appreciably affecting the 410 and the 660. Here's where we have this low velocity zone, so it doesn't exist so much over here. It's more pronounced where we have the low velocity region. So one interpretation is that it's water related partial melt, and then the 520 even starts to become a bit more apparent in this region. So the question is this the scar of the far plume as it went through and it's now somewhere else, perhaps under the Red Sea, it's been suggested to be. And but there's little evidence for a current thermal anomaly under this area. So in a sense...
What was the alignment of that section?
This section is running this direction. But there's another, in the paper there's a plot in an orthogonal direction too. And so in the old view, we had broad stretching and distributed strain and something that looked like this, the far plume, and now sort of a new and continually evolving picture is that we've got strain that's really focused, sharp variations, which I would argue are associated with melt punctuating through this. We've got this broad low velocity zone underneath the region, no obvious thermal anomaly at depth. And going shallower, the way we can reconcile the MT and the seismic, especially the anisotropy, is that we've got these interconnected sills throughout the lower crust, but then we've got a vertically oriented dikes and feeders towards the surface that are actually oriented very well with the crustal strain field, which makes sense. And we're starting to get this sort of picture of what's going on under afar with these isolated bits of continental slivers also in this region as the whole area is breaking up. So I think the observations are the fingerprint of Roger's ideas and other people's, Mark also recent work on magma assisted rifting. These upwellings, which probably originate from the larger superplume, which is below 660, so that it looks now like there's these isolated fingers coming up in different regions. These thermally erode the lithosphere, perhaps alongside some pre-existing weaknesses or thin spots. And that obviously that leads to magmatism and dike injection. And then we're seeing this crustal thinning over very, very short length scales, especially in northern afar. And so, some concluding remarks. So I think our seismic toolbox for looking at melts getting a lot better. It requires these long-term data sets and in areas, as Doug described, in subduction zones or mid-ocean ridges. I think the anisotropy is a useful tool, and I apologize that we really sort of neglected attenuation so far, but I think together anisotropic attenuation is maybe the way forward to make our life even worse. And there's a very clear trade-off, though, getting at actual volume fractions, which is something that John Blundy and other petrologists are severely disappointed to hear, is that I'm more interested in aspect ratio than the volume fraction. And something I didn't get time to talk about is there are lots of regions where we have really pronounced low velocity zones in areas that haven't had any tectonic activity for a long time. The Seychelles is a good example. We get 15% velocity reductions down to 180 kilometers. And there hasn't been, the plume was there 60 million years ago. And so in a paper with George Helfrich, we've argued that this is it can be explained by sulfide melts. So another time I'd like to talk to you about that. And I think by combining MT and seismic is really a step forward. Attenuation needs to be included. And then the other thing, I guess, listening to all the talks this week, is something we're doing in oil field setting is actually linking fluid flow simulators and geomechanical simulators to predict seismic properties. And I think based on what I've heard this week, we can start doing that for looking at the effects of melt in the upper mantle and the crust. I think that'd be an exciting way forward. So I'll stop there. Thank you.
very interesting work. Yeah, approach and the results are very fascinating. But I think when you talk about geometry of the melt, I thought the geometry corresponds to more or less mesoscopic.
No,
Rather
no. With effective medium on it, that's one. We have a hard time telling the scale.
yeah.
So a line series of dikes would look very similar to aligned melt films. And one way, and again, we've done this in oil fields very successfully, is to look at the frequency-dependent nature of the anisotropy.
Yeah.
But it also requires the medium to be poroelastic.
Yeah, but either mesoscopic or grain scale is important when you want to interpret.
Yeah. No, I agree.
But can I ask one more question? So the regional variation of melt signature is, to me, very impressive. Like East Pacific rise, as far as I understand it, there's not much evidence for aligned melt.
Well, we so
anisotropy can be attributed to solid.
in a paper a while ago, we argued that there is evidence for aligned melt on the marginal LAB, but because it's a fast spreading center, it's subhorizontal. So SKS wouldn't be sensitive to it, but we looked at shear wave splitting in a source at the ridge going off to different stations. And what we tried to first do was explain the amount of splitting using the predictions that Don and Blackman and I had for lattice preferred orientation, and that wasn't enough. And we had to add a tilted low angle TI medium helped that. But that's not proof in itself, but I think something like that's needed to explain our observations.
Andrea?
A simple question. Once you stripe out all the effect of the melt aligned in the crust, do you still need some melt alignment in mantle for explaining the Ethiopian data?
Yeah. Oh yeah. Yeah, definitely.
And you need it to be how?
In the main Ethiopian rift, it's got to be vertically aligned. So what's interesting is like under Butajira, which is on the western flank, not at the rift axis, we get 3.5 seconds of shear wave splitting. We can explain about 1.5 of that by mantle flow below. We can explain about 0.5 seconds of it from the crust. So there has to be something in the uppermost mantle below that area.
Planar vertical layers parallel to drift in the mantle too.
That would be our interpretation. Yeah.
Wow, lots of people. Just a sec. Can we have you?
Do you have an interpretation for the widespread low velocities at 220 kilometers and then changing above that?
No, not really. I think what's happening is you're getting, so what Ryan Gallagher's work at Southampton showing this, and the tomography with Cheng and Anna, is showing these tendrils coming through, and I don't know how good an interpretation this is, but they hit the less permeable lithosphere, and it's all flowing towards Arabia. That's my interpretation of it. I just think of this as big carpet of low velocity material that's density driven towards the northeast.
Doug, did you have a question?
Yeah, my question is, if we think there's pretty intense anisotropy there, then how do we do tomography? Because does your tomography assume isotropic velocities? So there'd be the possibility of really large artifacts in the tomography.
Yeah, no, Ian in his PhD thesis rotated the shear waves into the fast and slow orientation, and then redid the tomography. And there's a really clear difference. We're mostly sensitive to the fast shear wave if you assume isotropy, because you're looking at the leading contribution. If you don't rotate, you're going to just pick the fastest wave on average. But the problem with the slow one is you're getting contamination from the coda of the other wave a lot, and the orientation has to be done quite right. But he had a very, very clear difference. I can't remember what it was. It's in his thesis. We never published it because we didn't feel it was well enough resolved. But there was a very clear difference between shear wave tomography in the fast direction and the slow direction.
Yeah, and then it would also affect P waves, of course. So, and then as a function of the incidence angle. So there would be a whole bunch of effects.
No, it's something that needs to be done.
Sure.
Yeah, I had a question about your interpretation then. So, so you want to flow sort of northeast in the deeper part of the array, right? Below 200 kilometers or something.
Yeah.
So, but you showed evidence for a lack of evidence, or evidence against the transition zone changing thickness. So is it just that there's no hot material in the transition zone? It's all above it? I didn't quite understand. If you think there's a...
Well, it's to what degree things are thermal and chemical in this area, I think is the big question.
So the interpretation is there is in fact hot plume material in the deep mantle, but it's not...
Or density-driven material. I'm not sure. I don't know whether it has to be hot or not. But
it's not changing the...
I mean, it seems to be coming also more from Kenya and Tanzania. And there's really anomalous volcanism in those areas too. So I don't. It's outside of my field to know, to what degree chemistry is affecting this. But certainly below afar, the transition zone does not seem to be appreciably warm.
Awesome. So when you have this small aspect ratio melted collisions, and then you propagate elastic waves through such a medium, what is the actual range of frequencies you operate with practically and associated wavelengths? Is it low frequency in the sense that wavelengths compared to the size of the...
Yeah, that's an implicit assumption in the whole thing, is that the seismic wavelength is longer than the length scale of the inclusions, on the order of 10 times. But it is an interesting point in that why sort of teleseismic surface waves do not reveal this sort of structure detail, because you're dealing with the wavelengths as big as the whole rift area, whereas when we're looking at the crustal earthquakes, we're getting up to sort of 10 hertz. The body waves, we're getting P waves up to 1 hertz, half a hertz, that sort of length scale. So we get better resolution because we're dealing with higher frequency waves.
I mean, if you do this, you refer to some earlier work in mechanics, right? Budiansky, deriving effective media, right? This from sort of this microstructure. And is it an issue for you, since there are some further developments where you do when you start varying frequencies, right? And this effective characteristics they become frequency dependent.
You get squirt flow. Yeah.
Especially when you increase it to that extent, when the wavelength becomes comparable, right?
Yep. Yeah, and the shear wave splitting is very sensitive to that if the medium is porous. So if the seismic waves are high frequency, there's not enough time for the melt to communicate with the other pockets, whereas it's low frequency, there is enough time, and so actually you get a transition, and that characteristic transition in the amount of shear wave splitting can be used to infer the length scale. But we haven't been able to do that yet.
It's in a similar, because you emphasized inclusion on your last slide that inclusion and detonation is...
Yeah, it's all related to that, yeah. So that's true, yeah.
To include not only frequency dependence of wave speed, which is this question, but also to pick up effect of continuation.
Yeah, it's all interrelated, yeah.
I think we should continue any further discussion over lunch. Before we thank the speaker again, I'd like to say that it's been a long morning and a long week. I think all these talks have been fantastic. We have one more talk after lunch. If you're feeling exhausted and not sure you're going to attend, let me say Jerome Neufeld gives outstanding presentations. I think he's got some amazing experiments, and I would recommend that you stick around for that. John Rudd will give some concluding remarks, and then we'll wrap it up. So let's thank the speaker once more.